All right, boys and girls, welcome back to the drive-through for a three mix. Yes, this is my third try on this, but now I know what I didn't know before, and that's probably the most important lesson to learn. So, the hard part for me on this question is find the largest interval such this is a differentiable function. So that's going to be step two. Step one is to find dy dx. Now we're going to have to do this implicitly because we got this is not a function of x. So let me rewrite the equation. Now let's take the derivative of both sides with respect to x. Well, the derivative of tangent with respect to x is secant squared of that function, and then the derivative of the function, which is 1 dy dx. The derivative of x is just 1. So if we solve for dy dx by dividing each side by secant squared of y, okay, you get dy dx is 1 over secant squared. So dy dx equals cosine squared. Yeah, 1 over secant squared is the same thing as cosine squared. You might have to think that through for a second. All right, now here's where I got hung up. It's like find the largest interval such that y is a differentiable function of x. So we're going back to the original function. That's the first thing that screwed me up. So how do I write y as a function of x? If it starts out like that? Well, I want to isolate the y. So how do I get rid of tangent? Well, I take the tangent inverse. So you get y is the tangent inverse of x. Here's where I needed help from my mentor, Mrs. Brown. Big ups to Mrs. Brown. I was like, I don't know. I feel like y equals tangent inverse of x is a function that, and I graphed it. It looks like this. It goes on forever in each direction. I feel like it's differentiable and continuous everywhere. Well, it's not. It's if you go back to pre-calc, okay, and we never graphed tangent inverse. It's only defined as a function from negative pi over 2 to pi over 2. And just so you know, that's the same for tangent inverse and sine inverse. The reason why is if it's not, it wouldn't be a one-to-one, and that wouldn't make it a function. Now, just so you know, to make things complicated, cosine inverse is defined between 0 and pi. So they both have a 180-degree range where they do not repeat values and therefore remain one-to-one, okay? So that's where this part comes from. You might have to see me about this, and I can tell you right now, I will not put that on your test because I didn't teach it to you in pre-calc, but that doesn't mean it's not a good homework problem to do. All right, so now let me do the part three. Part three is the trickiest part, but the thing about part three is you actually do know how to do part three, back from our analytic trig struggle in pre-calc. So write dy dx as a function of x. So we have dy dx is cosine squared of y. Well, they want it as a function of x. So notice that we know that y is the tangent inverse of x. Okay, so what does that mean? Let's take it means tangent of y is x. So if I go to a right triangle, we take the tangent of angles. So the tangent of that angle is x. Well, that means that uh, opposite over adjacent is x. Okay. So we want the cosine of y. Actually, we want cosine of y squared. Remember that these are the same thing. Okay. So how do I find the cosine of y? Well, I got to find the hypotenuse. So hypotenuse is, well, 1 squared plus x squared equals h squared. So h is the square root of 1 plus x squared. All right, so what is dy dx? It's cosine of y squared. What's cosine of y? It's 1 over radical 1 plus x squared, and we want to square that thing. And that's where this book comes up with 1 over, oops, hold on, not radical, 1 over 1 plus x squared as the derivative. The derivative could also be called 1 over 1 plus x squared. And the reason why is that y is written as a tangent inverse function of x. So super tricky problem, but I assigned it, so I wanted to give you help with it. I don't think there'll be anything that difficult on any of your tests, but that doesn't mean you won't see it moving forward in life. I hope this helps. I hope I can figure out how to stop recording. Boom!